thing that I'm going to ask is, my computer is a horrible conversation partner. So please, like, unmute yourself, ask questions. I will try to monitor the chat, but I don't promise to actually be able to catch everything in it. So just unmute yourself, ask a question. I won't consider it rude, and then we can just keep going until we're done. Okay? Okay, so I talked about who I am. I'm at the Applied Physics Lab, which the US has a whole bunch of these university affiliated research centers. So as I was saying, I've left academia and gone into industry, and I am happy to talk to any of your grad students or postdocs afterwards about what that transition's like. My email's right there. So, and presumably this talk's being recorded, so you can go back and take a look at that. So all of this work is is based off of 2 papers. As I was telling Thomas earlier, I will be focusing primarily on that paper, and then time permitting, I will get to the second paper. And the collaborations here are Ben Dees. He is actually a graduate student at JHU in pure mathematics. He's a differential geometer. I believe he's on the job market this year. So look out for him if that is the type of thing that you were interested in. He is excellent. Much of this work could not have happened without him. And then Corey Lohman and Andrew Gerhardt are 2 colleagues at the Applied Physics Lab. Okay. The first half of this talk is going to be as I said in my abstract, you don't actually need to know what a neural network is in order to be able to follow this talk. The first half of this talk really is going to be explaining what neural networks is. I'm not going to be able to go into any sort of detail. I only have 20 minutes for this chunk of the talk, but it should give you a rough idea of the types of things that we are looking at and the types of things that we are trying to work with. And then we can go from there into the results of some of my papers. So neural networks for mathematicians, because we are not dummies. The general structure of a neural network, let me change color here, is I have some sort of an input space. So this is the data that I'm taking in, and this is of a very high dimension. The toy examples that I will be presenting at the end of this talk, P is 784. So if you just stop and think about it, if I'm just going to take zeros and ones, so the unit cube in 784, that cube has more corners than there are particles in the universe. Any sort of consistent, thorough sampling of this space is not going to be possible. So that's, when we're talking about image classification, oftentimes we're talking, so the reason I'm calling 784 small is because it is some of the most basic image classification examples, real world data sets we have for image classification. If you want to get into anything more complicated, the problem just becomes even bigger, or P becomes even bigger. But to give you an idea of the types of data we're working on, we don't have to work on data that big, but that's the size of the data that we're going to be working on eventually in this talk. Okay, so I have some large dimensional image space, and then I have some small dimensional output space. Now, I have, maybe this is one dimensional where this is a yes, no, is it a cat, is it a dog? Maybe it's a couple dimensionals that I'm kind of regressing along. I'm kind of trying to match a few regressions. Usually D is much smaller than P. And the problem here really is I have this data that is lying in this immensely large space, and I want to be able to find or identify and then mimic the pattern that kind of the surface that this data is lying along, where surface is some large dimensional object. So how do I do this? Sorry, was that a question? So the way that I do this is that I start out with a whole lot of hidden layers. And what this is trying to do, what this is trying to do is solve a type of problem called dimensional reduction. And I'm going to put that in quotes in case somebody wants to just kind of look up keywords in the machine learning literature and dig into them later on. One of the things that this is trying to do is trying to go from very large dimensional space where I have some sort of a surface with, some sort of key characteristics. I'm going down to a low dimensional space, which is going to give me the answer that I'm interested in. I need to be able to do some sort of dimensional reduction. And so the standard picture you see is something like this with the with the white circles and the blue lines, talking about a neural net, where each circle is an activation, some activation applied to a affine transformation. And this is called, and the circles are called perceptrons. All of this comes from an attempt to mimic what we think is going on in a brain, human, rat, fruit fly, like basically to mimic the behavior of neurons. I personally find that neurological analogy very, very opaque, maybe is the best word for it. So I'm going to be talking about it in terms of what's going on in that hidden layer is a bunch of linear algebra that's layered with a bunch of activation functions that reduces dimension. And the reason I'm going to do that is because when I'm talking about linear algebra, I can talk about kernels and images, and that I understand rather than the inputs and outputs of various neurons. So that's the perspective I'm going to be taking. So what is a hidden layer? So a hidden layer is I have some, oops, now I need to change my color again. There we go. Is some sort of a affine transformation, as I said before. And it has, and then it's combined with some sort of an activation function, where the activation functions are, the reason I've written it this way is the activation functions have one input and one output, but I want to apply the same activation function to every element of this affine layer. So I'm just going to apply it down the diagonals. It's a slightly sloppy way of talking about it, but I think just saying activation function composed on an affine transformation without having this messy diagonal matrix, just it makes a little bit more intuitive sense. But for a mathematician who wants precision, this is what we want to be thinking about it as. So X here is my output of the previous layer. Where previous layer could be the 0th layer, so that's my actual inputs. A is what's called a weight matrix. And B is called a bias vector. Okay, so again, and sometimes the popular types of activation functions are things like ReLU, which if I have X is less than 0, is 0, and then it is X. Otherwise, another one is the sigmoid function, which is equal to 1 over 1 minus e to the minus x, if I've gotten all of my minuses correctly, which is basically the logistic PDF. You can also have things like the step function. And what we're doing with the activation is, so what we're, the essence of what we're doing is that this is going to do a linear transformation. And this is going to separate into classes. So what the ReLU is doing, so ReLU is my, that should be a plus in the denominator. Thank you. Yes. So what the ReLU is doing is saying, okay, everything that's in the kernel, or that's, I can take my space, I can separate I can find the kernel of my linear transformation, and then everything on one side of it is set to 0, and everything else is the identity map on it. So I'm kind of separating based off the linear transformation. What the sigmoid is doing is, again, I'm going to take a look at the kernel. Everything on one side of it gets assigned a probability of greater than 0.5, and everything or a score of greater than 0.5, and everything on the other side of it is going to be assigned a score of less than 0.5. So it's various ways of just separating my data into two classes. And there's other activation functions that are out there. They'll all do the same type of thing. So, right, so this is basically what I said. So if I take a look at the ReLU, if this is my A, each of my rows, right, each of my rows I could think of as just the coefficients of a linear regression. Each of my rows there, again, is just going to be my constant term in my linear regression. And what this is going to do is when I set this equal to 0, it defines a P minus K hyperplane. This is just linear algebra. And all it's doing is it's saying that the ReLU is going to zero out certain linear combinations of the beta i's, just from taking the kernels. So I'll have an example like this. And the nice thing about the ReLUs is that so each of the ReLUs, each of the layers is going to correspond to one of these guys, and it's going to do a separation. Okay, this side's the blue, this side's the orange. And then the next layer is going to give me that, and the next, etc. Sometimes I'm being a little bit sloppy here because you can also do this with just one layer. I'll show you an example of that shortly. But essentially what I'm trying to do here is I'm trying to take a linear approximation of my data, of whatever my data manifold is, and trying to figure out what side of this linear approximation each of these bits of data lie on. So what I'm going to do next is I'm going to actually pause here for questions while I switch screens and show you how this works. Okay. Can you see what do you see? Maybe I should ask that. Am I sharing the correct screen?
Yeah, we can see the different states combining through some mappings.
Okay. So you are seeing the screen that I'm kind of rotating my mouse around.
Yeah.
Okay, sorry. And there's normally a green outline around it, which is somehow missing this time. So thank you for. Okay, so again, this is that same type of situation that we had before, where all of my blue states are sitting on the inside and all of my orange states are sitting on the outside. And I want to build a classifier that's going to separate out the blue from the orange. And I'm going to do this because I've played with this data before. I'm going to do this. I think this is the right way of doing it. I'm just going to let it run. Oh, wait, sorry. My activation needs to be ReLU for this to work. And it's not figuring it out for some unknown reason. That's strange. It was figuring out when it was tanh. This is the problem with trying to do live coding on, even though this isn't actually coding. There we go. Except that it is not showing the, okay. So the thing that was supposed to have happened, and let me just do it this way. And this is the problem with random seeds. But the thing that was supposed to have happened is that this circle was not supposed to be a circle. It was supposed to be hexagonal. Or not hexagonal, septagonal. And it was going to be a septagon because what I have here is I have 7 of these different neurons, each with a different ReLU function attached to it, each of which was going to be defining a different side of the hexagon. Or of the septagon, rather. I don't know why it is not doing that now, and I would rather not debug that on the fly while giving a talk. When I'm teaching the class about AI, about algorithmic bias, one of the things that I will go about is I'll say, well, instead of doing these two, if I was to take X1 and X2 and try and do it, then it will have my machine. Well, let's just do it. If I do this and I ignore these two, and let's say I do something like this. What I've done is, because if I didn't know that my data actually looked like two concentric rings, so I had no reason to know that x squared was the right transformation that I needed to do to be able to learn the data correctly. And I just did the naive thing, which is, it is the standard thing to do. It's just to not transform your data before you feed it through. You get something that does a pretty good job of fitting the blues inside and the oranges outside. But because it hasn't actually learned the data manifold, because you don't know what the data manifold is, it's going to end up with these weird errors. And that was, and I want you to kind of keep this, I haven't actually learned the data manifold idea in your head as we go through the rest of the talk. So let me go back to sharing again. Okay, so I just did that demo. Are we all good? Like, I'm seeing Thomas nod his head. I'm not seeing other questions. So I just wanted to pause and make sure. Okay. So this is going back to that picture that we just had from the TensorFlow playground. Actually, I will just maybe put a plug in here that the TensorFlow playground, if you want to get a feel for what works and what doesn't work in machine learning in general, is a really robust tool. A, you cannot break it. B, it has an awful lot of knobs that you can turn if you're trying to figure out, how does learning rate affect things, or how does the number of hidden layers affect things, or what do different activation functions do? It gives you a very good idea of what types of what the effects of different things are, where, unlike in real life, you actually know what the data manifolds are. So it's a fun place to play. Okay, so, oops. Right, so why am I kind of going through this? Why do we build these really complicated neural networks? So when I'm doing a linear regression, and when I have a 47-dimensional input space, and so I want to kind of find the best line that passes through that data, I can do a linear regression, and that will kind of give me a plane that passes through that data. But that doesn't take into any sort of account of the fact that the data may not lie on a plane. It may actually be curved. And the entire point of, not the entire point, but one of the strengths of machine learning algorithms is that it does do this piecewise approximation. Or you can change things to kind of get a smoother approximation. But you can actually approximate a surface that your data is lying on. And that leads us to the data manifold conjecture, which is saying that all of our data, always, in whatever situation we're in, lies noisily around some manifold that is embedded in my input space. And the problem is that I don't know anything about that manifold. But what I'm doing is I'm going to allow it to have enough parameters or enough flexibility to hopefully learn it. And that's the goal here. And now, for those of you who are statisticians in the group, or those of you who spend time maybe working with economists, this is probably raising your blood pressure, because the thing that's going on in the back of your head is, if I don't know the manifold, which means I don't know the data generating process, how on earth am I saying anything rigorous about anything? I want to acknowledge that complaint, and I want to table it, because that's or rather, I would say, if you're having that complaint, please email me and I want to have a discussion with you because I want to figure out how to do this better as well. But that's not the subject of this talk. Oh, I'm going to go, and this is where I'm going to transition to kind of pure math a little bit. So I'm going to work with a very special class of neural networks where the entire purpose of this particular architecture is to learn what the data manifold is, to learn a good approximation for the data manifold. So these are called auto-encoders. And they have cousins that are called variational auto-encoders. And also, another cousin is a generative adversarial network, or GAN. But all of these guys have a very similar architecture, and they're trying to do a very similar type of thing. I'm going to focus on autoencoders because that's the particular thing that I've been working on. But these results will translate to other areas as well. Okay, so what I want to talk about is autoencoders, or these types of things. So the key thing there is that there's an input space, and there's two networks. There's the encoder and the decoder. And what I'm doing is I'm taking my data manifold that is sitting in here. Actually, let me just say the data that is sitting in here, hopefully on a manifold. And it's sitting in there, and I am mapping it down to a low dimensional latent space. And then I'm reconstructing it. And then I'm mapping it back up to an input space. And so that hopefully the reconstruction looks like the data. Okay. And we can say more than hope. We can actually train our loss function to force the reconstructed data to look like the reconstruction to look like the data. And that's the purpose, is that I am taking the data, pushing it down to low dimensions, and then embedding it back into the high dimension space. And that's going to give me the data manifold that was the conjecture underneath. That's how these are supposed to work. Oh, right. So why is this special? Is that I can hope, I can hope that the F-enc is some sort of, okay, well, hold on. Let me back up a second. I'm going to set some notation. So I'm going to say F-enc is equal to the function represented by the encoder network. So the encoder is just a combination, it's just a composition of affine transformations and activations out. So this is a function, and I can talk about this as a function. And the F-dec is going to be the function that's represented by the decoder network. And then yes.
Yeah, so just a question. So my sort of understanding what you're doing here, your reduced dimensional space is picking up the manifold. And then
one hopes. Yeah.
One hopes. And then your encoder is sort of adding noise back on.
No.
Okay,
No.
okay. So
no, thanks for asking. Yeah. Go ahead. Yes. So my encoder is taking my data and it is decomposing it into a low dimensional space. And my decoder is just taking what it's learned and re-embedding it into high dimensional space. It's not adding noise back on. it is hoping to be able to, so what it's, in some sense, what it's doing is trying to learn the dimension of the data, which is a, well, no, I don't want to say that. It's what it's saying is that it's trying to find the best, whatever this low dimension here is. Let's say this is some RD. Right? It is trying to build the best d-dimensional approximation of my data. So I'm not going to add noise back on. What I'm going to minimize is the distance between the original point in input space and
okay. So your decoder is going to be some sort of smooth mapping back to the original space.
Yes, exactly.
Okay. So, so you know that's fine. I'll just say though, adversarial networks often really do add noise as well, though. So they're typically taking extra random inputs to do that extra step.
Right. So So the generative adversarial network, the second step, the second node that is adding some noise to be able to be able to sorry, no, there's a generative model, and then yes, one of them, and I don't remember if it's the equivalent of the decoder or the equivalent of the encoder that does add some noise in order to be able to increase the prediction ability. That's solving a slightly different problem than the one I want to talk about here. But adding the noise seems to have a lot of, it improves performance and generalizability. But yeah, but that's a different issue.
Mm-hmm. Yeah, cheers.
Okay. Okay, so I have the function that's represented by the decoder network, and then I'm just going to let D to be my data points. That's going to sit. Well, no, I'm not going to say that it sits in me. It sits noisily around M. So my training goal is that, you know, if I knew for a fact that all of my data lay on a manifold M, then when I compose these two maps, I really literally get a identity on my manifold M. Okay, so the reason that I really like these guys, the reason that this is different from what the conversation about GANs was just a few seconds ago, is that in an autoencoder and in a variational autoencoder, what I'm really doing is it looks like a coordinate chart. I have some sort of manifold. Let's assume that my data actually lies exactly on the manifold for a moment. So this is not a realistic statement for most cases, but for now, let's just make that simplifying assumption. I can take some sort of coordinate chart on this, which is almost always possible because my D is just a discrete set of points. So I can create a very strange sort of single open set that contains it all. And then what I'm going to do is my coordinate chart is going to go to some R something where I don't know the dimension of my manifold. I don't know if it's 2. I don't know if it's 16. And all of this is sitting inside my input space. Points inside my input space are always going to be called X. My encoder is going to map it to a latent space. Points inside of my latent space are always going to be called Z. And then my decoder is going to send it to a reconstruction space, which I'm going to call Y. And I can, so if everything works theoretically correctly, I will have that when I compose this with that, I really do have a coordinate chart and its inverse composition, and I'm doing exactly what I want to be doing on a manifold, and when learning the geometry of a manifold. And that's the hypothesis that I wanted to be testing and playing around with in these experiments. So one thing to note is that, and this is an important note, is that the training process really is discrete. So I am trying to fit a discrete set of data points to a discrete set of data points. I know nothing about the actual manifold structure, or just from this, there's no constraint that forces me to actually learn the manifold structure. So for instance, if I have a autoencoder that takes this set of inputs, set of outputs, nothing that is constraining one function, one of the functions from learning this, and the other one from learning that. I could have an encoder having learned the left-hand side and the decoder having learned the right-hand side, and that's as far as the training is concerned, I've minimized the differences between my input and my output. They're exactly the same in this case. It doesn't care. But once something like this happens, I stop being able to generalize, because I now have a different, if I now give it a point sitting over there, my encoder and decoder have very different ideas of what's going on in that space. Okay, so keep that in the back of your head. We're going to come back to it. The first question I want to ask is, how far does this function that I'm talking about, the composition of the encoder and the decoder, how much does it actually differ from a projection map? The projection map is what I would want it to have, if it's actually properly learning my manifold. A few things. How do I test if my encoder and decoder are actually projection maps? I can take a look at their Jacobians. So I can take a look at the Jacobian of my encoder, which is the big 784 dimensional one. I could take a look at the Jacobian of my decoder, I totally misspoke there. This first Jacobian is the encoder come first and then the decoder. So it's going straight through the autoencoder in the correct order. That's a square matrix. So I can really talk about a Jacobian being a square matrix and have all of the nice properties of square matrices. This is 784 by 784. It's basically the input dimension by input dimension, usually big and ugly. I can take what I'm going to call J sub L, which is the Jacobian going from the latent space back to itself. This is the advantage of the latent space being small dimensional, and therefore matrix computations on this are relatively easy to compute, but it does have the disadvantage of now doing the decoder first and then the encoder. So I've kind of swapped the order of my autoencoder. So we have to worry a little bit about how much is actually preserved when we do this. Actually, a projection, everything should be fine, but it may not be a projection. And then the other thing to notice is that so this map here, if that map is a projection, I can take and order my eigenvalues. I'm just going to call this a vector of my eigenvalues, where I'm just going to go from the highest eigenvalue down to my lowest eigenvalue. And my first D should be A non-zero. And also if it's a projection, my first D should be 1. So that's the quantity that I'm going to be testing for, because that's the quantity that I can actually measure. Oh, and you turned your camera on. Does that mean you have a question brewing?
No. I just decided that you're the sort of person who probably likes having faces to look at. So
it's fine. I'm happy either way. Okay, so as I said before, there's a computational simplification. The Jacobian on the input space, so the one that's going through the autoencoder properly, is enormous. So trying to compute eigenvalues on that is not something that you should attempt on your laptop. It is something that I do. I have access to something that kind of splices up computations into multiple streams, and it still takes several hours on that machine to be able to do it. Ben, the grad student, tried to do this on his laptop, and his laptop just started making very worrying noises, so he stopped that computation. So what do we do when we don't necessarily have access to huge compute power? We can look at the eigenvalues on the latent space. So, changing the direction of the autoencoder. And the reason there is that if my map is close enough to the identity, or if it's exactly the identity, I can show by chain rule that these sets of eigenvalues are the same. Or maybe I should say this, then the top D of these Let me rephrase that. I apologize. The top D eigenvalues of my big one are going to be exactly the same as the eigenvalues as the D eigenvalues of the small one, and that's just chain rule. And so we don't exactly have this condition, but if we train for MSE loss, it means that we're close to having that condition. So as an approximation, this might be good enough to be able to use. Okay, so experiment 1, and I may not get time to do the second experiment, which is fine. I have an autoencoder. My inputs here are MNIST digits. And my outputs are, whatever the reconstruction of MNIST digits are. So MNIST digits they're like 70,000 handwritten digits, 0 to 9. It was originally commissioned by NIST, which is a US government organization on setting standards for industry and technology. And the entire point of this was so that the Postal Service could automate being able to read zip codes. So it didn't have to have a human in the loop for that. And it's been very, very successful. MNIST has become a standard for people who are trying to understand image classification because it is so well understood at this point in time. So I'm using the MNIST data set. This is why the number 784 comes up. I think it's 28 times 28, I believe, is 784. So it's 28 pixels by 28 pixels. And they're all grayscale. So the values are between 0 and 1 for each of the pixel values. Okay, so what we expect from the lemma, remember, I said that, we expect, and again, this should be a top D here. Right, so these top D should be the same, and we get this by minimizing my mean squared error. And what we actually observe is, okay, it's not too bad. The one thing to keep in mind is that L2 distance increases linearly with dimension. So what I've done here is I've just taken an average. So I've taken whatever, if it's a distance in 3-dimensional space, I've just divided it by 3, just so that I have a standard way of comparing across dimensions. Oh, I apologize. I should go back here and I should say one more thing on this slide. What I did is I trained 19 different autoencoders. So my latent dimension varies. I can't write. From 2 to 20. So when I'm talking, and that's the only thing that I've changed. That's not quite true, but for the purposes of this talk, we want to think about this as that being the only thing that I've changed. The rest of the architecture is more or less the same up to the bits that I need to change in order to be able to support this. Because my last layer has to now have different dimensions. But I don't want to get bogged down in that. But so I'm projecting down to either 2 dimensions, 3, 4, all the way up to 20. And I want to see what's going on across these dimensions and how the behavior of the autoencoder changes. Okay, so back to this side. When I'm taking average, so here, this is my 2-dimensional. So I take whatever that distance, L2 distance is in R2 space, and I divide it by 2. Over here, my distance is 20. So I take whatever the L2 distance is, divide by 20, just so I can have an apples to apples comparison. And what I find is that, yeah, as as my dimension increases, I get closer and closer and closer. My MSE error decreases, and the L2 distances between the eigenvalues also decreases. So at higher dimensions, I really can just, I'm pretty good about being able to substitute the lower dimensional matrix for the higher dimensional matrix, and I don't have to worry about the computational differences in the eigenvalues. Okay, what else do we expect? If I am I wanted the actual question that I want to see is how far am I from a projection? So if what I'm doing is I am going from my large dimensional input space down to my onto my latent space, and I'm not actually learning the manifold in there, but I'm learning all of my latent space, and then projecting the entirety of the latent space back into my reconstruction space in some weird way, then and if it's a projection, then I would just have the dimension is equal to my trace of my maps. Now, if I'm actually projecting onto the manifold, there's going to be some point where I'm going to reach the dimension of my manifold. I'm going to stop increasing, and then I will flatline, because I don't need to learn anything more because I've already learned my manifold. Okay, what do we see? We're not quite at either extreme. Okay, so this would be learning all of my latent dimension, all of my latent space. We're not doing that, but we're not, but we're not kind of cutting off and flatlining either. We're somewhere in the middle. So there's some extra learning going on, but at some point it does stop trying to learn everything. Okay, what else do we see? So here I have taken, I've split my MNIST data set into different classes. So I've split my, 1 through 10. We see a couple things that are interesting. Class 1 behaves very differently than the rest of the classes, which there's a lot of reasons why we expect that to happen. I don't want to go into that too much. But what I want to talk about here is that if I compare the geometric means of the eigenvalues and the arithmetic means of the eigenvalues, I see that they're relatively similar, which means that I'm not somehow having my results being strongly skewed by outliers in one direction or the other. And the reason that I have to kind of do this type of analysis is because, again, these are 70,000 data points. There's not a good way to go through each of these in any sort of systematic, more rigorous analytic way. Other thing that we can take a look at is I can take a look at the map yes, I think this one, I take a look at them in both directions. I can take a look at F-enc composed with F-dec, or the other direction, because I have both the Jacobian on L and the Jacobian on I sitting around there. I can take a look at their determinants of these Jacobians, or for the I case, I can take a look at the product of the top D eigenvalues. And what I can see is that there's very few points where the maps are locally orientation reversing, which is good. You know, I mean, even here where it's high, it's only 6%. And at the issue with, with latent dimension 2, latent dimension 3 is that there really does seem to be not enough space. There's too much noise happening there, that it's collapsing things down to too few dimensions for it to be able to learn anything properly. So all sorts of strangeness happens there. And that's pretty consistent across any way we cut it. But eventually, as we kind of get down lower, into higher dimensions, it's actually able to learn things properly, and we don't have any orientation reversing behavior, which is good. It's actually learning some sort of manifold structure. And then I want to go finally to here. So what we expected is that, if the network, now I'm not looking at a point. I'm now trying to look at some sort of open set. If the composition of the networks was not giving me the identity in this open set as functions, then the network's not going to generalize. And we can test that. So the way I would test that is if this was the type of thing that was going on, where I was where I had one function was learning one thing in one open set and the other function was learning the other thing on the other open set, then an increase in my MSE error, what we would see is an increased MSE error, but only on the test points. So we can test that. And so what I regressed is, I should define a few terms here. Let me do this in a different color. Here is, I'm calling it a volume form. This is a product of the my eigenvalues. And the n is corresponding to the latent dimension. This is a 0 if it's a training point. It's a 1 if it's a test point. Okay, and I'm doing everything in log scale just because that seems to be what the data wants me to do. So what I'm regressing here is I'm saying, if I am a training point, then the last two terms disappear. And I really just have those first two terms that I need to worry about. And I can take a look at what the coefficient is for that. But by having this chi factor here, I can now worry about it also being a test point. And then I can separate those two out. So if I'm a test point, then my slope becomes beta 1 plus beta 3. And my intercept becomes beta 0 plus beta 2. Something that's not reported here is that the beta 0s and the beta 2s are basically all 0. So I don't have to worry about that. That's not reported here, but you'll have to take my word on it or look it up in the paper. But what I'm seeing is, what I'm plotting here is this test slope here is beta 1 plus beta 3. Again, for a while, I'm just not doing a whole lot of learning. There's just too few dimensions for me to get any sort of traction. But after some time, again, like starting kind of in that slightly after 10 range, I start seeing that my test slope, my MSE error on my test points really does increase as my as the log of my eigenvalues increases. So the more different my two eigenvalues are. Sorry, let me rephrase that. The more different the stretching here and the stretching here is, the greater my MSE errors on my training point, or on my test points. And that's what this is showing. So, this, if you're truly applied and trying to kind of build better machine learning models, this then raises the question of, do we want to be training on this as well, trying to force that to be closer to 1 as an additional constraint on our learning models, etc. These are all questions that are very valid to be asking. I have concerns about just the calculational speeds of being able to calculate these eigenvalues. That it's going to slow down the training process significantly. There are trade-offs there to be made, and that's trade-offs are a very applied question. That, as a pure mathematician, I want to say that's above my pay grade and not worry about it. I have 10 minutes. I can either pause now and open for questions, or I can try and show a different set of results.
We normally try and leave about 5 minutes for questions. So I don't know if you can go like halfway house, or just like a summary of what you mentioned.
Okay, so let me go through the second set of results quickly. Okay, so now the second set of results, and these are really kind of fascinating. I have the same 19 pre-trained autoencoders. The difference here is that they're pre-trained. So whatever I did in experiment 1, I'm keeping those networks. I'm not doing any more training. I'm saying, okay, now we've learned maps. And now I want to see, what did these maps do really, really, really far away from the training data? So what I have is like 8 or 10 different random pixel values that are giving you. I have like a Bernoulli distribution. I have several Bernoulli distributions. I have a normal distribution. I have a uniform distribution, et cetera, et cetera. And I feed those through. And depending on the dimension, I either get a relatively good reconstruction, or I get these fascinating, a relatively good reconstruction, not of the images that I fed through, but of the original data set. Or I get these fascinating generalized characters. that at a high enough latent dimension, it seems to have learned something about what writing is and is trying to reproduce this, which is kind of fun. So for instance, I've done this for 2 seeds. I've kind of classified my the various distributions I fed it into, bright, moderate, and dark distributions. And the reason I've done that is because the brightness of the input distribution seems to have some sort of effect on the brightness of the output. So the way you want to think about this is the top here for each of these is input, and the bottom is the output or the reconstruction. I'm just going to put recon there. Okay. And then I kind of show you what it is as D goes from 2 all the way to 20. So let me just kind of walk through this slowly. So, okay, so I'm going to, right, so the first thing to notice is that these guys are darker. The next thing to notice is that for the first, I don't know, we can argue about exactly where, but I would say, somewhere between 7 and 8 dimensions, it is reconstructing a number. Right? It was trained on numbers. My poor autoencoder knows that it's supposed to bring me a number. This is like, and it is doing its best to bring me a number. Okay, it brings me a number. Sometimes it takes a look at all of the data and brings me back the same number. Sometimes it takes a look at all of the data and brings me back different numbers, but it brings me a number. And then eventually, and here's where I want you to remember the picture of where it's not learning all of the latent space, but it's not flattening off and like I would expect for a true projection to do. And eventually it's learned too much. And like maybe starting here, it brings me a generalized character. So so I have now, what I've done is that I'd never learned the actual, I didn't properly learn the dimension of my manifold. I learned because I'm doing all of this, but I don't know what my true dimension of my manifold is. And this is why, people who are interested in what happens if I don't know the data generating process, I want to talk to you. And therefore I'm reconstructing other things because these are other things that have happened. Other thing that's interesting is that if I go across, and I realize it's hard to see in the very light range, but at least you can see it in the light and the medium. It seems to learn the same character all the way across, and I've just fed it noise. And then keep a look at what that character is for 20 or for 19. If I give it a different seed, that character changes. So very, very unstable, but it's learned something. Anyway, that was the second set of results.
Okay, excellent. So yeah, we'll probably take some very quick questions now. If anyone's got any burning questions, raise your hand or I'll just unmute. So yeah, I was interested. I think actually Anna can go first. She has a hand.
Oh no, I think that's just a clap.
Oh, it's just a clap, excellent. Yeah, I was just interested in the manifold aspects. It seems like he's starting to get towards like differential geometry and kind of also you're having to do like a kind of minimization procedure almost. Do you have like any idea about like where you take that kind of train next in terms of understanding the kind of geometry of the manifolds and kind of would that help improve these algorithms, do you think, by using some of those like tools about the classification of different manifold types and geometries?
So the main barrier that my grad student pointed out and kind of really struggled against, and then we couldn't find a good answer, was that a lot of those things of classification of different manifolds, etc., a lot of those require us to know something more about what the actual manifold is, and B, to be able to do calculations on curvature. And calculations on curvature are extremely computationally expensive. And that's kind of where we are hitting a wall right now. Now, it is quite possible and maybe worth doing of just for a small case for kind of in order to kind of be able to come up with some sort of theoretical bounds to be able to do those calculations on curvature and know that it's just going to hurt, but it's going to hurt once. But so that's definitely an approach to be able to take. But if you want, so for instance, if I want to be able to understand what's going on with the projection map when I'm a little bit away from the data manifold, which is where most of my data lies, I'm going to have to be able to compute geodesics to a data manifold, or geodesics from the input to the reconstruction along the function that I've learned. And those geodesics require second-degree derivatives, and things start getting really, really messy really, really fast. So that's the type of thing that I'm talking about, is just being a computational barrier. But yes, there is, if we could come up with those computational barriers, a workaround, or just decide to bite the bullet once and just do it, that's definitely an area for progress, is working about, thinking about what happens to these tangent spaces along these geodesics, so we can really talk about whether or not it's projection. The other, yeah, let me just leave it there.
Yeah, we got Owen, I think, was having his hand up.
Yes, just wondering, it's not particularly well-formed question, but so the view you've taken in terms of these as functions of the inputs, and thinking in terms of Jacobians, so you're sort of thinking that the underlying manifold is smooth in some sense, but of course the actual functions are parameterized by some enormous parameter vector, weight vector for the machine learning people. And of course, we know quite a lot about the gradient of the parameter vector. It's used when you fit these things. And I mean, so I suppose the obvious question is, what can you take from that to actually tell you about the smoothness of your manifold, if anything?
Oh. So I want to separate out two things, because I think maybe they're being confused, or maybe I'm just misunderstanding your question. So there's the actual manifold that the data lies on, and then there's the learnt manifold that we're learning. And anything that the gradient vectors that you're talking about is going to give you information on is the learnt manifold, not the actual manifold.
Yeah, so no, I suppose I was thinking more about so that with thinking about the net as some sort of it's an approximation sort of function encoded by this separate sort of parameter vector. So it's encoded by this thing, so so there's information there about, for example, how smooth it is as an approximation. But that information is not particularly easy to get hold of. But nonetheless, you can sort of you can speculate that maybe there's something useful there from the the gradient with respect to the parameters.
So you're saying, let me just try and do this concretely. So in my example, I'm looking at MNIST. So I have this kind of 784 dimensional space. That's my initial input, and I have values between 0 and 1 for each of those.
But then But then you might you might have a sort of 2000 dimensional parameter vector, which is encoding the, which describes the encoder and the decoder, depending on how many layers you've got.
Oh, I see. So you want to take a look at that entire function in terms of its weight and basis.
Yeah. So I suppose I'm sort of thinking, because one way of constructing a nice projection is to restrict yourself to, small combinations of smooth functions, whereas we're doing quite the opposite here. We're taking very, very large combinations of quite irregular sort of functions.
No, so I had not thought, that is a very interesting idea of thinking about what we're doing with the gradient descent in terms of the actual parameters of the weight. No, that's not something I've thought about at all. I mean, right now is not the time to talk about it, but I would love to have an email conversation with you if you have some like concrete thoughts in that direction.
It's not a question I have an answer to. I'm sorry to say that.
No, but if you want to kind of flush that out a little bit more, that might be an interesting thing to at least think about. If not, yeah. Yeah, sorry, I don't have a.
No, that is fine.
A bit over on time, but there is one more question. It will all be on the YouTube channel, so Attila.
So yeah, nice talk. Thank you. Maybe it's a really, I don't know, weird question, but so what I understood that you have some data points, and then you assume that there's some manifold that splits these data points into multiple parts, and then you try to reconstruct this manifold, and then map it back, because that's like a nice way of doing it. And my question is, how do we know that there's only one manifold and not like multiple?
So, we don't. So first of all, we can have multiple connected components. Like that's absolutely fine. There are lots of questions we can ask about which manifold is the best to kind of think about how this data sits around, and as soon as we have that best question, there's questions of best along which axis. Are we doing best along MSE, which is assuming a Euclidean metric? Are we doing a best along a different metric? Is there a different perspective for the application that we're looking at? Yeah, that's the data manifold conjecture is very much in a conjectural state.
I was like thinking of something like where we have like an XY axis, so it's just like a 2D thing, and then you have, I don't know, like 5 different functions in there, which is defined by points, and then if you look at the figure, then you can sort of see what the manifolds are, because like from outside you see it, but like how would you learn those different like manifolds just from having the bunch of points, basically?
So maybe the thing to do is to go back to this picture, which maybe is what you're trying to get at. So if I'm looking at a situation like this, where it's just an XY, and I have the one class lying on one manifold, and another class lying on a different manifold. So blue is lying on this circle, like and the orange is lying on this annulus. And those are 2 different manifolds that it's lying around. And so what I'm trying to do is I'm trying to learn kind of the boundary between these 2.
Yeah, but what I mean is that for 2, you can find, like there is a boundary between the 2, but if you have, I don't know, like a sine function, and then maybe an exponential function, and then some random polynomial. So those are the 3 things where you have the points clumping up. And you can see like, oh, there is like a line there, and another line there. But how would you learn those just from having the vector of points, like XY points?
So again,
that would mean like you have multiple manifolds.
Yes. So again, my belief is that as long as you are having a vector of points that are so what you're going to end up doing is you're going to end up with, oh, hold on, let me go back to sharing the other screen and draw your picture that you were trying to do. I stop sharing here. I think I understand your question now. One second, there we go. So you are saying, if I have one class sitting like that, and one class that's sitting like that,
Yeah.
and oops, sorry, wrong button, and another class that's sitting like
maybe a
that.
circle or something in the.
Okay. Or well,
Yeah.
okay, I've drawn a line already.
Doesn't matter, yeah.
Is that okay?
Yeah.
And
it's like you have three manifolds which are one-dimensional.
Yep.
And
then,
the
issue there really is going to be, what I will be able to do is I will be able to, I'm going to, so let me just, I'm going to do some sort of piecewise approximation where maybe I can get that and that if I have enough layers and enough wiggle room. And I will be, and I mean, all I am doing at the end of the day with this is I am taking my two-dimensional space and I am finding kernels of matrices and saying on one side of it is brown, on the other side of it is red, on one side of this is blue, on the other side of this is red. So but I'll end up with some sort of an image like that. I will not give you a functional form. It will not be the right functional form. There's going to be lots of mistakes, as you can see kind of in this area here. Right, in this area here. Oops, that was the wrong tool. Let's try that again. Area here, there's just like all sorts of stuff going on, and I'm not being able to break things up apart properly. And these areas of overlapping data are they are a nightmare. There may be other ways of pulling this out. Another way of pulling this out, which in this case might actually work because your input dimension is small, is if I take this and I embed this into a much larger dimensional space, then all of a sudden I could separate things out. So instead of being in a three-dimensional space, I embed it into a seven-dimensional space. Instead of being in a two-dimensional space, I put it into a seven-dimensional space. Then I might be able to put the different functions on different layers and then be able to do the splicing more nicely. But things like that require your input space being small enough that you have the ability to do that rather than starting with a really large input space.
I was just thinking on, if you have just XY points, how would I set up anything like this optimization? What am I trying to optimize to get these 5 curves out or something? Because the like a neural network is just like a function approximator. So, so how would I get out from a bunch of points 5 different solutions, or like 5 different neural networks?
Right. So you may not be able to do it from R2. But if you go from R2 to R7 and then back down to R2, you might be able to do it. I'm kind of picking 7 as an arbitrary large number. I don't know that 7 is the right number for this. But those types of solutions are usually, for this type of problem, those are the types of solutions that I've seen be successful.
Okay. Yeah. Oh, and also there was another question that I had. So sorry for just holding up. If you go back to 23, like slide 23 or something like that. Oh, maybe one more. Yeah, here. You said something with ones, and then I was just looking at the curves, and it was just a curious thing that 1 and 7, which are made up of one line, are like
that's exactly
better,
what's
and
going
then
on.
8, and then 8, which has like two holes in it.
Yes,
is the worst one. So it's just like a curious thing.
1 is much more than the other ones, but so there have been lots of ways of trying to learn the actual manifold, as opposed to where I'm focusing on is what the autoencoder, what the neural network has learned about the manifold structure. And all of those attempts to learn the actual manifold indicate that 1, which is, as you've said, just one line, has significantly lower dimension in the in the pixel space than any of the other ones do.
Oh yeah, it's just one line.
Yeah, exactly. 7 is another one that has a moderate amount of dimension. I don't remember what the issue with 8 is.
Probably, I mean, I don't know. It's just like it's too. It looks like it's related to the number of holes, probably.
No, it's not. It's not
No?
that simple. I wish it were. Yeah. But yeah, no, but one stands out in terms of how different its dimension is. Like its dimension range, I don't remember the numbers off the top of my head, but its dimension range does not overlap with the dimension range for the other ones. You know, I think these guys are all in the 11 to 16 range. And this is in the 7 to 8 range. Like people think that this is probably a 7 or 8 dimensional manifold. This is a like it's just very different than the other classes.
It's just a curiosity. Probably it's totally wrong. So
yeah,
what I was saying. Yeah.
I mean, so the reason I'm saying it's not has to do with the number of holes is that, you know, as important for the purpose of this parameterization is how similarly do people write their ones and their do I write my one versus you writing your one? You know, somebody writes a one like that and versus somebody writing one like that. Oops, that's a really bad one.
Wow. Probably my ones would confuse the neural network with the 7s. So.
Right. You know, there are people who write ones like that and 7s like that, and this causes all sorts of problems. So it's more than any sort of topological aspect of the physical number.
Also
I suspect the similarity from person to person of that variation plays a bigger role.
Yeah, also the topology of the actual number, like how it looks like, is maybe totally different than the topology that the 8 is in this high dimensional space. So it's not related. So nice.
Okay, excellent. Well, yeah, that was some very stimulating discussion and a great talk. Thank you very much, Susama, for joining us today.
Thank you for your time.
Yeah, it's been excellent. Cool. Well, enjoy the rest of your day and might see you around.
Many thanks indeed.
Bye. Thank you.
Thanks, Susama.